Hugo.
All right, thank you, Hugo. Thank you, Guillaume, for organizing all of this. So the Caribou plugin, it's a plugin I actually did for my PhD, and is now currently being used in the Mimesis team, so the research team I'm in right now. So basically, during my PhD, I had to work with different kind of elements. I was working to simulate the liver using hyperelastic models, and I was researching for some exotic methods such as meshless methods and immersed boundary methods. And typically, with SOFA, you would have, I mean, what's typically used in SOFA is you would have different kind of force field for each of the element type you have, which was becoming more and more difficult to do in my case for my PhD. So I created the Caribou plugin, which I will now overview. So it's the plugin is separated in two parts. The first one is actually the SOFA plugin. So it's using SOFA framework, and you can load it inside your simulations. And there's the second part, which is a library, the Caribou library, which doesn't depend on anything but the Eigen library. So I will go through first the Caribou, the geometry and the topology modules. I'll just swap slide. Right. So, like I said, I had to design different kind of elements. Here I will only present you the basic ones that you all know about. But yeah, the idea was to rapidly create a different kind of element and have different orders and dimensions. And here the inheritance that you see is not a virtual one, it's a compile time one. So it's using template, C++ template to do it. And the reasoning for this was to allow the compiler to optimize most of the code so that I don't have to do it myself. I will show you an example of how I would create, for example, a quad element. It is, I will just, okay, so there's different slides. Okay, so yeah, basically I will, in order to do, for example, this quad element, I will have to simply implement four things. First, I will need to put some compile time information about my element, which is the number of nodes known at compile time. In the case of a quad element, it will always be 4 nodes, and the number of quadrature nodes at compile times. Now, in my case, for meshless methods, where elements are in fact point clouds, you would have sometimes a number of nodes known during runtime. And for immersed boundary elements, you would have a number of quadrature nodes here that is known during compile times, following where the surface is cutting the elements. So in the immersed boundary methods, the elements are only partially filled, they are cut by the boundary. So in this case, you will have runtime information. And then I will simply define 3 functions. The shape functions of my elements, the shape derivatives, and the Gauss quadrature nodes and their respective weights. And by simply defining these 4 parts of my element, this allows me to have various tools. So for example, here either in Python or in C++, I can create rapidly a quadratic hexaedrons given a set of nodes. From this, I can get the center point. I can get the world coordinate of any barycentric coordinates here. I can get the inverse of these transformations. I can get the Jacobian of the transformation at any given local point. So again, in barycentric coordinates. I can test whether some word positions is contained inside my element. I can also compute intersections with other kind of elements. I can interpolate field functions at some internal points, and I can also integrate different field functions over the elements. Now, if you want to get fast simulations, I would advise to use the C++ one, as most of these functions are header-only, highly inlined code, which should get optimized by the compiler. Let's see some more about Caribou. So the topology model uses the geometry model. So it will define a mesh which contains data on each of the nodes, and it can contain many domains of your complete mesh, which will have information on each element. There's also in Caribou an hash grid and a VTK loader to load different kind of meshes. So let's see an example of a domain. This is in Python. So using Mesh.io, which is a very cool Python library that allows you to read many kind of different meshes. So let's say I'm loading right now a tetrahedral mesh, also a displacement vector. So the displacements over each node of my mesh computed, for example, with Sofa. And then I will create the Caribou mesh and domain over this. Here there are no copy involved, so it's the reference that will be passed to Caribou. I could then embed a set of marker nodes, for example, where I would like to have the displacement over these positions. And then I will simply embed these markers within the domain and interpolate the displacement vector to get the displacement at the position of the markers. So this is a quick examples. You could also simply read or get the barycentric coordinate over each of these embed markers. So for example, for each markers, you will have the element of the mesh that contains these markers and its corresponding barycentric coordinates. There's also a small example of how you would assemble, for example, a Neo-Hookean material residual. So here R is the residual vector. This is basically the same things as the add force methods that you often see in force field of Sofa, but written in a very concise way. And you can do exactly the same in Python again. So this is the Python example where you will assemble this residual vector using this function. And then a very quick overview over the SofaCaribou. So I've implemented different kind of force field. Probably the most used in our team is the hyperelastic force field, which is independent from the type of elements and the type of materials. It will use the geometry and the topology model of Caribou to do this. There's also a couple of linear solvers using Eigen. And now the cool thing about Eigen is it allows you to have different kind of backends for the solvers. So for example, Paradiso, you also have Super LU and different kind of solvers. So in Caribou right now, I only have the default Eigen solvers and the Paradiso one from the MKL library. There's Newton-Raphton static solvers and only 2 hyperelastic materials. I didn't have time to do more, but they are quite straightforward to implement with this library. Quick example. So for example, this is a scene where you have the solver part with the LLT solver. You have an hexahedron container, the materials, so the infundant here, and the hyperelastic force field, which has the hexahedron as template. If you don't specify a template here, it will default to the container it found in its node. You can find, oh yeah, I think it's the old version of my slides, but if I go back to the first slides, you can go on the Caribou that reads the doc. where you will have every component of the plugins with the different parameters you can pass to them, and some examples, and in most of these components, some Python bindings for each of them. So don't hesitate to go there if you want more information.
Oh my God, it's a timing which is a gold timing. Just 1 second after the ring, after the bell rung. Perfect. Thank you, Jean-Nicolas. Is there any question about the Caribou plugin developed by Jean-Nicolas and this modular approach to compute continuum mechanics in Sofa? Oh, I see multiple users are already typing. So you should, while the questions are being typed, just you should write an example of writing a quadratic hexaedra integration in Caribou, right? That's what you showed on one of your slides.
Yeah, in Caribou it's already done. If I go back here, the only problem if you want to do it in Sofa is you have to have this topology container, which I didn't have time to do. But it's on my to-do for this year. So basically, you would have to do a topology container for quadratic elements, and then the hyperelastic force field will work.
All right.
Without needing any changes.
Okay, that's because that will be super interesting. I know already for partners at University of Florida. I don't know. I did not see Jörg. He was here earlier, but there was Jörg Peters and there was also Rui Langao. So I think for them it would be super interesting to get a look at that, and maybe I think there would be. I mean, is that possible to openly contribute to your plugin, Jean-Nicolas?
I'm sorry, what?
Is that possible to contribute to your plugins?
Yeah, of course. It's you can go on GitHub. You can create pull requests, issues if you want to contribute. Right now, like I said, I would very like to have these quadratic containers and things like that. So if someone wants to look at that or to create their exotic elements, it would be a very nice test for the Caribou library. So.
Okay, thank you for the information. I saw that Pasquale has a question. Pasquale, you are in a listen only mode. Can you type the question you have, or can you type it to me if you'd like? Eric, in the order at the question, is there a difference of performance with the existing implementation of in Sofa?
So no. From I mean, I didn't do a proper benchmark test, but I tried, for example, the hyperelastic force field using tetrahedral elements, which we also have in Sofa, and for 200 milliseconds time steps simulations, I think I have maybe 5 milliseconds more than the one of Sofa. And that was not actually coming from the implementation. It's just that in the hyperelastic force field, I actually accumulate one time the stiffness matrix, which I then copy back to Sofa, and I think the the small overhead times is coming from that. But the nice thing with this is if you want to optimize the force field, you only have to optimize one, which is the hyperelastic force field, and it should actually work for any kind of element types. So this is quite good.
Yeah, great, thank you. So if you optimize the constitutive law, then independently from the type of element, it would work.
Yeah.
I'll ask two questions in one because I think you could answer them quickly. Both. First, Pasquale, he was wondering about, is that possible to recover strain stress information, to have access to strain stress information from Caribou? And the same for Younes, he was asking, and is that also possible to couple Caribou with constraints?
Okay, so for Pascal, yes, you can. I'm not sure if the Sylvanak or the different hyperelastic materials have Python bindings, but I think so. So you could access to, basically the materials have three functions: the internal elastic force W, or energy, its derivative, and its Jacobian. And you can access those directly using the Caribou topology. You can interpolate the displacements, the gradient of the displacements, and you could use the bindings of the materials to get this strain or stress information at any given point inside the domain. And for UNES, can we use constraint? So it's actually the same thing as SOFA at this point. It's only a force field. Now, the mapping, you would use the barycentric mapping, for example, or the mapping from SOFA. I'm planning to do mappings which, again, are independent from the element type. Which is also on my to-do, but it will allow you to get this mapping matrix J automatically from the topology.
Thank you again, just in time for the questions. Thank you also. You have the opportunity to ask further questions to Jean-Nicolas in the breakout rooms after this numerical methods session. Thank you again, Jean-Nicolas.
Thank you.
And yeah, so congratulations again for this new PhD degree that you got, and for this very nice piece of work that could, I think, be very interesting to finally integrate completely into SOFA, so that could become some kind of default way of creating force fields in SOFA.